Hello everyone, this is Matt Lau, and today we are going to cover your introduction to radiology training. A little bit of history on radiology. William Conrad Röntgen was a Bavarian physicist who discovered X-rays in 1895. And then in 1901, he received the first Nobel Prize in physics for this discovery. And as you can imagine, this was a huge change in not only dentistry, but medicine in general. So how do we generate X-rays? Well, an X-ray tube is simply just a vacuum-sealed glass enclosure that we surround with lead. So that lead shielding that's around that glass tube is going to have one hole in it, and that's where our actual X-rays are going to come out of that tube. Inside that glass tube, you're going to have a cathode and an anode. Your cathode is a tungsten filament wire within a focusing cup. So it's really much like a filament in an incandescent light bulb. Then on the other side of that, you're going to have your anode. Your anode is going to be a slab of either tungsten or any other type of heavy metal, and around that heavy metal, it's going to be embedded in copper. So what happens within our X-ray unit itself is our X-ray unit is going to take our incoming power and it's going to convert it into two separate streams. One of them will be varied in different amounts of current, which flow through that high resistance wire or that filament that we spoke of in our cathode. That current that flows through the cathode is measured in milliamps. The second stream is going to be very high voltage, and that's going to be measured in kilovolts or kVp, which stands for kilovolts peak. That voltage is applied across the gap between the cathode and the anode. So as we heat up that tungsten wire that's in our actual filament, that's going to cause that wire or that filament to start emitting electrons. So we're going to have a focusing cup that is going to allow those electrons to, for lack of a better word, pool up and then precisely hit our positively charged anode in the exact spot that we want it. This process will generate two types of energy. Number one is heat. 99% of the electricity we're using to create X-rays simply goes to heat. And then 1% of that electricity will actually generate X-rays. So our X-rays are going to come out of our housing through a small opening called a collimator, which is going to restrict our beam down to less than 2¼ inches at the patient's skin surface. We're also going to use an aluminum filter at the opening of our tube head that's going to filter out any of the X-rays that are of no diagnostic value to us. Then we're going to use a lead line cone that will actually collimate our beam down even farther to make sure that none of our X-rays are going anywhere that we don't want them to go. So this is a design that came out in 1913 created by General Electric, and believe it or not, it is still the exact same technology that's used today. So how do our kVp and our MA work together within our X-ray tube? Well, our low voltage stream, or our MA, flows through that heating element like we were talking about earlier in our cathode. This element is in a small covering called a focusing cup. So as that guy gets hot, it's going to boil off electrons. So normally those electrons would simply just pool up into that focusing cup, but that doesn't happen. What happens in an X-ray tube is we're going to use our kVp to push those electrons out of that focusing cup. So our high voltage, or our kVp, is going to be applied across that gap between our anode and our cathodes. This is going to cause our negative electrons to be attracted to our positively charged anode. So our kVp is going to be applied across that gap with so much potential, and it's going to cause a stream of electrons to go speeding across that gap with great velocity. Our focusing cup is going to be negatively charged, which is going to repel those electrons So they're all going to push to the center of that cup and create that nice tight beam that we're looking for. This is a diagram of an actual X-ray tube head. So what's going on is this is my filament. So this is the part that I'm going to get super, super hot. When I heat him up, or when I apply my MA, my milliamps, through this stream right here, what's going to happen is that is going to generate lots and lots of heat, which will then allow my electrons to pool up right here. So then I'm going to apply my KVP, where you see this dotted line going across. I'm going to apply my KVP across there, which will generate that difference in potential to cause those electrons that are being pulled up here to come shooting out, hit my anode, and when they hit my anode, that's where we're going to generate our X-rays. So these electrons are going to hit that tungsten target so hard that they explode into a shower of high energy photons. So these photons, as I said earlier, are what's going to create our X-rays. They're much like a visible light photon, except that they contain a lot more energy, and they can actually penetrate opaque matters. However, items with varying density can block some of those photons, which will then cast a shadow on my X-ray film, or if I'm using a digital sensor, it'll cast a shadow on that as well. The energy of those X-rays is going to be controlled by my high voltage or my KVP. So as I increase that KVP, the X-ray photons that I'm producing are going to have a shorter wavelength, which means they're going to pack a lot more energy because they can penetrate deeper into tissue. The number of photons that I generate is going to be controlled by my MA. So the more milliamps I run through that filament, the more heat I'm going to generate, thus the more electrons I'm going to generate. Most of your newer X-ray units are going to come preset from the factory, but you'll see many older X-ray units out there that are going to allow you to vary your KVP or your MA, or in most cases, be able to vary both of them. But on your newer units, normally the only adjustment that you're going to be able to make is your actual time. So your modern units are going to have a digital controller on them that's going to use tenths of or 1/100ths of a second as a standard measure of time. But your older units simply use the 60 hertz sine wave that's coming out of the outlet as your timing pulse. So when X-ray beams hit an object, they have a nice uniform distribution with very high energy. They're absorbed then by a greater or lesser degree depending on the density of the tissue that they encounter. So as I said earlier, all these photons coming out of our tube are going to be in a wide range of energies. Our low photons are going to be easily absorbed by soft tissue, which means they're not going to hit my film or my sensor. So all I'm going to do is give my patient more radiation than I need to. When it comes to prescribing X-rays, dentists should be doing it, prescribing X-ray after they've done their clinical observation of the patient. So it used to be that every 6 months, no matter what, you'd go in and you would have X-rays taken. Well, that's no longer considered acceptable. Doctors should be evaluating patient needs before they actually take X-rays and to decide if X-rays are even needed at that point. So radiation has 3 different effects on organic matter. Those 3 effects are classical scattering, the photoelectric effect, and the Compton effect. When it comes to classical scattering, what happens is the X-rays are going to enter the human body, and they're going to be in a nice form, basically flying in a tight group. But what happens is they're going to come in contact with the actual atoms of the human body. So that photon's going to come in, it's going to hit the atom. It's not going to have enough energy to displace the atom, but basically it's going to what we call tickle the atom. When it does that, it's going to actually release a second photon from that atom, and that's going to continue off in a different direction. The photoelectric effect is when that photon comes in, it has enough energy to actually knock the electron loose, and then the atom actually will absorb the energy from that photon. But however, now it's missing an electron, which then means it's going to try and steal one from a different atom. So this is basically going to create a positive charge to that atom, which is called ionization. When it comes to the Compton effect, this is where the photon is going to come in. It's going to have enough energy to displace that electron, but it also won't get absorbed. It'll just keep on zinging past and actually hit another atom. These three reactions aren't at all life-threatening. The molecular interactions of the alternate atoms can disrupt molecular bonds. However, new bonds will be formed. The radiation is also going to interact with the water and oxygen in the cells, which can actually damage DNA. The high doses of radiation to the entire body can cause some very, very acute effects, and long-term or chronic effects are going to come from repeated exposure. Your body's going to attempt to repair itself, but if the exposures are regularly or too strong, it's not going to be able to keep up. The important thing to remember is that the operators of X-ray equipment and you as a technician should monitor the amount of radiation that you're exposed to. So if you're going to be dealing with a lot of X-rays, we recommend that you wear what's called a film badge. Some of these badges need to be mailed back off to the vendor that created them, and the other ones are just going to be simply you plug them into a USB port and they're going to tell you what's going on. So the operator themselves should always be standing behind a lead barrier at least 6 feet away, and put yourself on as great of an angle as possible. Obviously, you should never hold a film while exposing it, and you should always make sure that lead aprons and thyroid collars are being used on patients while they're being used or while they're getting x-rays taken. But the amount of radiation that's put out by a dental x-ray is very, very minimal. The patient would have to have 25 full mouth series in a short period of time to increase the risk of skin cancer. So obviously the benefits of detecting diseases far outweighs the risk of the radiation. But again, you always want to make sure you're keeping yourself safe. Most people hear radiation is very, very dangerous. However, when it comes to the amount of radiation being put out by a dental x-ray tube, it's actually quite minimal. So based on a full mouth series, that's going to deliver roughly 18 microrem to the patient. A panoramic x-ray is going to deliver roughly 2 microrem. So we're not going to really get into what the equation is for microrem, but the important thing to remember is that the average person just being alive in the United States is exposed to roughly 300 microrem just from naturally occurring background sources. So as I said earlier, you can see that the output of these dental x-ray tube heads is very, very minimal. The nuclear societies determine the maximum safe occupational exposure for the whole body is roughly 5,000 microrem per year. So all these equations and figures that we're talking about, these are for the patient, so somebody who's directly in the beam. The biggest thing we're worried about when it comes to you guys out there is what's called scatter radiation. The analogy that they use here I think is very, very good. Where scatter radiation is basically if you were in a very, very dark room and you had a flashlight and you aimed it at the corner of the room, even the things behind you would be slightly illuminated due to the light scattering off of those corners and illuminating the rest of the room. So when it comes to radiographs, we're talking about the actual x-ray that's produced or what is produced on the film or on the digital sensor. There are two things we're worried about: density and contrast. And that's what's going to be tell you the quality of the X-ray that's being taken. So density is the actual blackening of the film after the exposure and after it has been processed. The blacker the area, the higher the density. So this is basically the ability of the film itself to stop light passing through it. Contrast is basically the difference between the blackening and how light the film gets. So how light and how dark is going to be your contrast. There's going to be 3 different factors when we talk about contrast: your subject contrast, your film contrast, and processing contrast. And we're going to get into all 3 of these. And then the last one is processing. If you have a processor where the temperature is too high, all their films are going to come out dark. If they have their temperature too low, well, then all their films will come out too light. In either way, the detail of that radiograph is going to be lost. And they should always be making sure that their solutions are fresh to work properly. Old chemicals are not going to activate that film properly, and you're going to get a call saying that all of my films are coming out cloudy. Cloudy films are a telltale sign that their chemistries are bad. So after that film has been exposed, it has to be processed. So even with the best technique, the best patient, the best X-ray machine out there, if their processor is not set up properly, they're going to lose all that detail on those films. So when it comes to our film, the film is just a blue tinted plastic that's got an emulsion over it. That emulsion is going to contain a gelatin, and in that gelatin is going to be silver halide crystals. These silver halide crystals get energized when they're exposed to radiation. So where there's a filling or a very, very dense bone, those crystals are going to have very, very low energy because the X-rays didn't hit them. The interproximal spaces, or if you have a cavity or soft tissue, again, it's very easy for my X-ray photons to get through. Those photons will then hit that silver on that film, which will then turn that film or those crystals black when I process it. So when my X-ray film is immersed into my developer, that developer is going to soak into my gelatin and react with my silver halide crystals. That reaction is going to create what's called silver and bromide. In the metallic form, those silver particles turn black. So then those black particles or those silver particles will be deposited onto the film, which will create the dark areas. Crystals that have not been energized are simply washed away by my fixer, which will then make my film turn white. So my developer reacts with the energized crystals to make them black, and my fixer simply will remove any of the crystals that have not been energized, which will then make that film turn white. So if a film is coming out too dark, it's either exposed, overexposed, meaning they're using too much radiation, or it's overdeveloped, meaning they have had it in the developer for too long, or they have their processor temperature too high. If their film is coming out too light, either they didn't expose it long enough, they didn't keep it into the developer or have it in the developer for long enough, or they had it in the fixer for too long. So our automatic film processors is a much quicker and much more consistent way of processing our films, provided they're keeping their chemicals fresh and that they're maintaining that processor, meaning keeping it clean. So within our processor, we're going to have a series of rollers or webbing that's going to guide my film through the chemicals. We're going to use a heating element to make sure that my solutions stay at a constant temperature. And in between my baths, I'm going to have a special roller that acts like a squeegee to make sure my chemicals aren't mixing together. The 2 most common failure points on processors are dirty rollers, meaning they just are not cleaning that processor once a week like they should be, or they're trying to save money and their chemicals are expired. They should be refreshing their chemicals at least daily. Most of your processors now, every time they put a film in, they're going to replenish the chemicals in that processor. But depending on the manufacturer and how they're using their processor, they should be changing their chemicals out completely every 2 to 6 weeks. And that's where they try to save money, and they run their chemicals longer, which will then weaken the ability of those chemicals to do their job, which will then, again, you'll get a call saying all of our films are coming out cloudy. So a diagnostically useful X-ray has some very, very specific qualities. It should be a combination of black, white, and some shadows of gray. Your contrast is a difference in colors to show the definition of whatever's going on in that picture. So the denser the object, the more it's going to block the X-ray beam, and the whiter it's going to come out. So your contrast is going to depend on the type of film you used, their processing technique, and the density of that film. So a film with good contrast is going to show the darkness of all the soft tissue, the lightness of the amalgam or the gold fillings that are being used, and then the subtle shades of gray in the nerve canals and the trabecular bone. Contrast of the film is determined by the thickness of the patient's bone and the density of his or her hard tissue. So these are some of the variables that the operator needs to consider when they're shooting X-rays. Density is another thing that's very, very important. Density is dependent on the following: the amount of radiation, how far away they have that tube head from the patient, the thickness or the tissue thickness of that patient, and how the film is developed. So as we were talking about earlier, the higher the MA, the milliamps, the more amount of X-ray I'm going to produce, which will then give me a darker film. The more I raise my kilovolts peak, or my kVp, the more energy I'm going to produce, which means my beam is going to be more intense, which means my film will be darker. So the farther the patient is away from the X-ray beam or the tube head, the less intense that beam will be, and the lighter the film will be. The longer the film is exposed to that X-ray beam, the darker it's going to be. So in most of your newer units, this is the one variable that the operator can change. So the quality of the film is called the resolution. So low resolution film is just like a low resolution television. It's going to look very, very fuzzy. A high resolution film will look very sharp and very, very crisp. So if the patient moves or the film moves during an exposure, they're going to lose resolution. However, a tube head movement won't cause poor resolution because the X-rays leaving that tube head are parallel with the tube head. So if the tube moves on a parallel axis, it's going to be fine. If it moves more on an angular axis, that's where it's going to cause actual shadowing, and you're going to lose detail on that film. So digital X-ray is going to be the latest technology. This has actually been out since 1980. It was discovered by a French student. The only downside was the early digital X-ray images couldn't be stored. They could only be printed. So this got a bunch of people working on it, a bunch of companies getting together with a lot of software technology, a lot of hardware development. And now in the US, digital X-rays were approved for use in 1990. So the downside to traditional film, actually there's many, is the time it takes to handle and retrieve patient's film. If it's got to be duplicated, you have your darkroom upkeeps and your maintenance. You have clinical errors. You have increased exposure to your patients. Film processors are not at all eco-friendly. And then you have your actual processing costs. So digital x-ray is a huge motivator in advancing a dental office. Biggest reason is digital images can be electronically transferred, basically just shoot them over the internet. You can take a digital image and you can insert it into a Word document. Digital image can be printed on just a standard high quality printer. You can again send it to another dentist and that you're not going to lose any quality. And these images can be manipulated, change the contrast, change the brightness. You can change all, depending on what the doctor is trying to see on that film, you can manipulate that image to give him the best view possible. Also, images are going to have a lot more detail to them. So that makes it ideal for patient education. Doctor can go into an image and he can magnify it to show the patient up close what's going on. So he can vividly show what's going on with the patient's caries or cavity from different degrees. He can actually measure any kind of periodontal bone loss, the contrast, the intensity, the brightness, even the color can be enhanced. It saves time for insurance claims because the doctor can simply just shoot it over the email. And that makes it easier for him to get pre-authorized, which means he can treat that patient that much faster. They're also going to limit clinical errors because once that image is stored into a patient's folder, there's no way of mislabeling it. They don't have to worry about it getting lost or put in somebody else's folder. They already know whose it is because it's labeled. And the biggest benefit over digital radiology opposed to film is that there's less exposure to that patient. This is referred to the ALARA rule or principle, which stands for as low as reasonably achievable. So what that means is that the patient gets just enough radiation to be of the diagnostic value to it. However, no more than that, so there's no long-term ill effects to that patient. So the biggest factor when it comes to digital radiology is cost. So over time, yes, the doctor is going to save money with digital radiology. However, the upfront costs are quite high. So these numbers are slightly off now, but in this equation, they're saying to buy 2 digital sensors is going to be roughly $20,000. The computer equipment is roughly $5,000. And then the training for the operators is going to be $2,500 for a total of $27,500. Now that number is slightly off because the cost of sensors have come down. Most offices don't need to buy any kind of new equipment anymore. Just most of these sensors simply plug right into a USB port. And most offices or most manufacturers out there who are selling digital sensors will come to that doctor's office and train the staff for free if they bought digital sensors. So in digital radiology, you're going to have 3 different systems in place. Your direct, your semi-indirect, and then your indirect method. So indirect methods are typically when a doctor first switches over to digital radiology. He's simply going to take the images he already has. He's either going to put them into a flatbed scanner or use a high quality digital camera and actually just take a picture of it. It's then going to be stored electronically in a digital format. Your semi-direct methods, this used to be the most common method out there, where the doctor's office would be using a photostimulatable phosphor plate or a PSP plate. These would store a temporary image of whatever the radiograph is. They'd use packs to hold these plates. They look a lot like just a standard traditional film. These systems were much more comfortable to the patient than digital sensors at the time, because digital sensors were much larger back then. They have now since got much smaller, so these phosphorus plates aren't nearly as common anymore. But these plates go into the patient's mouth just like a standard film would. They have phosphor crystals on them, which is going to temporarily store the digital image on those plates. They take the plates, they would put it into a scanner, which would then basically digitize that, put it directly into the patient's chart for the doctor. Transfer the plates to the scanner must be done in a dark room, or the plates will get erased by ambient light. So using these phosphorus plates wasn't a whole lot different than using standard film, other than the fact you didn't have to process them. The machine itself would do all the digital processing for it. Direct methods or direct systems are without a doubt the most common out there now, because the sensor size has come way down. The cost of these systems has come way down, and they're very convenient for the office. So this is going to take a digital radiograph using a sensor. The doctor's office can use the simple RIN type sensor for positioning. Obviously, we're still shooting radiation, so the patient still needs to have that vest, and all your FDA and ADA guides still have to be used. These systems, again, are very basic now. They can plug right into a standard computer, provided that computer has the software from the manufacturer on it. It'll automatically take the image, store the image, and move on to the next patient. When it comes to panoramic x-rays, your panoramic units are the x-ray units that actually rotate around your head. So this is a type of tomography, which comes from the Greek word tomos, to cut or to section. Tomography is a technique for digitally cutting a specimen open using x-rays to reveal interior detail. So this is exactly what your pano units do. It's the simplest form of tomography because it doesn't show any kind of 3D images. It's simply a 2D image. So our x-ray beam will come out fan-shaped, like a fan unfolded in a vertical position. This beam will project through a small slit through the patient, back then to the film or to the digital sensor. Our beam and our x-ray cassette, or our film or our sensor, revolve around the head in the same direction, while the cassette itself moves in the opposite direction. So what that does is it basically gives you a 2D image of the entire mouth in one shot. So because that film is fan-shaped, only the bony structures closest to my film are going to be projected onto my film or onto my digital sensor. The bony structures or any of the tissue matter that is closest to the x-ray beam, because that fan shape, will simply get blurred out. When it comes to your CT or your cone beam systems out there, these guys will actually produce a 3D, very high quality image. However, they use, in some cases, 4 times the amount of radiation to get these images. So typically these 3D images are going to be in oral surgeon offices. These units are very high tech units, and typically the only people who are going to be authorized to work on these or get any kind of technical support on these are going to be manufacturer trained technicians. So that concludes our introduction to radiology training.